Okay, welcome back to the second part of our section here for videos. So example 3, analyze and sketch the graph up. Now we have a rational function here, so now we're going to have some asymptote lines. So the first thing we have to do is identify our domain, which is just like identifying your vertical asymptote, so we'll take care of these two at the same time. X cannot be equal to plus or minus 2, can be everything else but that. And then that, just take off the slash through the equal sign because those are going to be my vertical asymptotes. My horizontal asymptote, notice that our x squareds are the same, so our ratio 2 over 1, that's going to be my horizontal asymptote. Since this is my horizontal asymptote, that's going to be my limit as x approaches both positive and negative infinity. Remember, that's our horizontal asymptote rule. X-intercept, take the top binomial, set that equal to 0 and solve. So that would be x equals positive or negative 3, but we're going to write these as points. Y-intercept, you got to take that GCF of 2 times the negative 9 and put it over negative 4. So that simplifies to 9 halves, so that's our y-intercept. All right, now we go to our first derivative. First derivative, find our critical numbers. We're going to have to do the quotient rule here. Here we go. So 2 times, we just basically remove that 2 out to the front. All right, your denominator, x squared minus 4 squared. That's your first. That's the original g function from the bottom. Then the derivative of the top of x squared minus 9 is just 2x minus the top function x squared minus 9 times the derivative of the bottom function, which is just 2x. So again, we can do some factoring here. We can take the 2x and factor that out. So you have x squared minus 4 minus x squared plus 9. So my x squareds are going to cancel. Negative 4 plus 9 is going to give me a 5. So the 2 times 5 gives me 20x on the top over x squared minus 4 being squared. So my critical numbers on the top, x equals a 0. From the bottom, x squared minus 4 equals 0. So my vertical asymptotes plus or minus 2, they're occurring twice. That's important now when I draw my number line, because the negative 2 and 2, I can subscript it with 2, but I put vertical asymptotes here instead of a tick mark to remind me that this is not going to give me a relative max or min. All right, so furthest to the right, let's check our simplified derivative here. Positive 20x divided by positive x squared squared. That's a positive region. Happened twice, will not alternate signs. Happened once, will alternate signs. Happened twice, will not alternate. So where are we increasing? Right where the plus signs. Where are we decreasing? At the minus signs. All right, now, but remember, these are vertical asymptotes. So I increase from 0 to 2 and 2 to infinity. I decrease from negative infinity to negative 2, then negative 2 to 0. Unlike the other problem, those were x-intercepts that were repeating, and therefore it decreased throughout that whole interval. So that's why we put those vertical asymptotes in here as dashed lines to remind us that we got to break up our interval. All right, relative max and mins at 0, we are decreasing and then increasing, so that's a relative min or local min. And again at 0, that's going to be that y-intercept we found at 9 halves or 4.5. So we'll put that in. Okay, now it's time to go find our second derivative. So we're going to have to use, again, the quotient rule. So our x squared minus 4 squared being squared, again, makes that to the 4th power. X squared minus 4 squared, that's your first function, times the derivative of the top, so that's 20, minus the top function 20x, times the derivative of the bottom. Now I'm going to do the chain rule here. So 2 out to the front, x squared minus 4 technically to the 1st power, then the derivative of the inside is just 2x. So again, we have some factoring potential here. We can take out a 20. We can take out an x squared minus 4. So you'll have 1 x squared minus 4 left here on the left of the minus sign. You'll have x times 2 times 2x. So that's that minus 4x squared right there. So if we combine like terms here, that's going to make this a negative 3x squared with a minus 4. So what I'm going to do here is I'm going to factor out the negative from these like terms, multiply it to the 20, which makes this now 3x squared plus 4. All right, so set the top equal to 0, but 3x squared plus 4 will never equal 0. So we have no points of inflection. But we do have critical numbers at plus and minus 2, but they occur 3 times. That's that vertical asymptote still there. All right, so we draw our number line with the 2 vertical asymptotes. Now here we have a negative 20 times a positive 3x squared divided by a positive x squared. That's going to make this a negative region. It occurred an odd number of times, so it alternates. Positive, then negative. So we concave up between negative 2 and 2, concave down from negative infinity, negative 2, and 2 to infinity. All right, so let's plot our points here and our asymptote lines. So our asymptote line right here at, we said horizontal asymptote y equals 2. We have one at negative 2, positive 2. Throw in our x-intercepts, negative 3 and positive 3. 4.5 for your y-intercept. All right, so everything to the left of negative 2 said it had to concave down and decrease. There's this graph, and same thing over here on the right side. It's kind of a mirror image. And then in between was a concave up. And it was also increasing from 0 to 2 until everything matches. So there's our graph. Okay, example number 4. All right, so let's domain. X can't be 2. Vertical asymptote x equals 2. Horizontal asymptote. Top is bigger than bottom. There is no horizontal asymptote. We'll probably have to find a slant asymptote. All right, x-intercept, factor the top. Well, that doesn't factor, so I'm going to complete the square, subtract over the 4. Half of negative 2 is negative 1 squared is 1. Wait a minute, this is a negative 3. So if we're going to be taking the square root of negative 3, that's going to give me imaginary numbers, so there's no x-intercepts. Y-intercept is positive 4 over negative 2, so that's 0, negative 2. So let's go find our slant asymptote. You can either do long division, x minus 2 divided into x squared minus 2x plus 4, but because that's a linear function on the bottom, we can do synthetic division. Take your x minus 2, solve it for x, which is 2, put it at the bottom. Bring down to 1. 2 times 1 is 2, minus 2 is 0. Don't worry about the last column. This is going to be a remainder value, and slant asymptotes do not want a remainder. So y equals 1x plus no constant. So that's our slant asymptote. So that's a line with a positive slope. So when x gets bigger to infinity, so does y. But as x goes to negative infinity, y goes to negative infinity. All right, first derivative. Oh, geez. Quotient rule again. All right, x minus 2 squared on the bottom. Start with x minus 2. Derivative of the top, 2x minus 2. There it is. Minus, okay, top function times the derivative of the bottom, which is just a 1. I don't see anything I can factor out between the two, so I'm going to multiply this out, distribute my minus sign, and combine like terms. So these two right here is 2x squared minus 6x plus 4. Distribute the minus sign, as you can see. Combine like terms to x squared minus 4x all over that binomial x minus 2 squared. So we can factor out an x on the top. So critical numbers 0, 4, and a 2, but that occurs twice. All right, so increasing and decreasing. Again, 0 and 4, and then the vertical asymptote with the dash line repeating twice. So looking at my function here, positive x squared divided by an x that's positive being squared, so this will be positive, negative, no change, negative to positive. So we are increasing from negative infinity to 0, decreasing from 0 to 2, decreasing from 2 to 4, increasing from 4 to infinity. Again, you have to break this up because that's that vertical asymptote. So there's the intervals I had mentioned. Increase to decrease, relative max or local max at 0, -2. That's our y-intercept. Decrease to increase, so at 4 will be a relative min. So plug in the 4 into the original function. That's what I did here and came up with 6, and there's my y-coordinate. To the second derivative. Oh boy, quotient rule again. So x minus 2 squared squareds to the fourth. Lead it off here. Derivative of the top, 2x minus 4, minus top function times the derivative of the bottom. So chain rule, 2 times x minus 2 times the derivative of the inside, which is 1. Oh, let's see. I see an x minus 2 that I can factor out. I see the 2 and the 2 from the 2x minus 4. I factored that out, so that'll leave me an x minus 2 there. So I basically have 2x minus 2's, one from here and one from here. And then we have our x squared minus 4x left over. So let's see, we're going to have to do some foiling of these two, distribute the minus sign, combine like terms, so x squared and minus x squared cancel, minus 4x plus 4x. Wow, we're just left with 2 times 4, which is 8 over x minus 2 to the third power. So our only points of inflection numbers that are not there are 2. None of them are there, but we still have to test the 2. It occurs 3 times. So this is a positive 8 over positive x to the third power. Positive on the right side alternates to minus on the left. So we have a concave up and a concave down. So from 2 to infinity we're up, from negative infinity to 2 we're down. Okay, so let's see. Vertical asymptote at 2, slant asymptote at y equals x. So y-intercept at 0, up 1, right 1. X-intercepts, none. Y-intercept 0, -2. We also had 4, 6. That was a max, so I want to plot that point. So concaving up to the right of 2, we must have to have a curve that looks something like this. Has to approach the vertical asymptote on the right going up. And then it has to approach the slant asymptote over here. And then the same thing's going to happen here with this relative min. We're going to approach that slant asymptote from the bottom and the vertical asymptote from the left. And there's my graph. Okay, example number 5. Oh, square root. This is going to... All right, here we go. I have, let's see, x squared plus 2. That's going to be positive all the time, so I don't see any domain restriction, so that's all real numbers. I do not see a vertical asymptote because we can't make that equal to 0. And my horizontal asymptote, well, let's hold off on that and see what we get. X-intercept is 0, 0. Y-intercept, 1 over the square root of 2. But wait a minute, nope. Let me change that. We can't go to this 2 on the inside because it's inside the square root, isn't it? So it's just going to be the same as the x-intercept. That's it. All right, so where is my limit going to be? So what we're going to do is we're going to divide everything in the bottom by the square root of x squared, which puts the x squared on the inside, and the square root of x squared is x. So this gives me 1 over the square root of 1 plus 2 over x squared. As x approaches infinity here, that's going to become a 0. So this is approaching 1 for all x greater than or equal to 0. And it's going to be approaching -1 for every x is less than or equal to 0. Because now when I go to negative x, this is going to be a negative over here that I divided by. Okay, so remember that square root of x squared? That's that piecewise function we talked about. Okay, so horizontal asymptotes at plus and minus 1, and those are your limits. So as x approaches infinity, y's go to 1. As x goes to negative infinity, y's go to negative 1. All right, let's go find our first derivative here. A huge quotient rule. The square root of x squared plus 2, all that squared, so we'll probably be able to simplify that. Square root of x squared plus 2 times the derivative of the top, which is 1, minus the top function x times the derivative here. So chain rule, 1 over 2 times the square root. Keep the x squared plus 2 on the inside. Take the derivative of the inside, 2x, and multiply that to that 1 that was up here, and that makes it 2x. All right, so we can do some canceling here. We can cancel the 2's. We can multiply the top and the bottom by a square root of x squared plus 2. So what that's going to do is going to cancel this out here and turn this just into an x. This multiplied over here will turn it into just x squared plus 2 times the 1. So here's your x times x squared right there. There's your x squared plus 2. This canceled out. On the bottom, well, now you're going to have the square root of x squared plus 2 squared times another square root, so that just raised it to the third power. Our x squared and a minus x squared cancel out. And okay, there's our first derivative. So critical numbers, none. Can't have the top equal 0, and the bottom can't equal 0. So it's going to increase everywhere. Positive 2 divided by a positive square root of x squared cubed, that's positive. So it's increasing everywhere, and that's your right-hand behavior, and nothing was there to change it. No decreasing, no relative max or mins. All right, second derivative, here we go. I changed that square root of x squared plus 2 raised to the third power. I'm going to change that to a fractional exponent. So this is going to be squared. This is my denominator, that's the g first, times 0, because the derivative of 2 is 0, so all this is gone. Minus 2, that's the top function, times, okay, let's take the derivative of this, bring down the 3 halves, subtract a 1, so times 3, there's your 3 halves, there's the 1 half as a power, keep the x squared on the inside, chain rule, take the derivative of the inside, times 2x. So let's clean this up. The 2's cancel. Negative 3 times 2x is negative 6x. Square root of x squared, times x squared plus 2 to the 1 half power. Let's see, well, this is going to become, now notice what I did here. I didn't cancel the 2's. I wrote this as 6 halves because when I divide like bases, I'm going to subtract my exponents. So this is going to cancel out the 6 halves to 5 halves. So negative 6x, so point of inflection is going to be at 0, and nothing here because we can't get that set equal to 0. So I draw my number line, there's the 0. Oops, negative 6x divided by positive x squared. So this is a negative, and this is going to alternate to a positive, so we're concaving up on the left, down on the right. So negative infinity to 0, 0 to infinity. Okay, so let's draw our asymptote lines, y equals 1 and negative 1, where x-intercept and y-intercept. And so let's draw our graph here. Okay, so we're concaving down on the right side. So we have to go and approach that asymptote here, and then we're concaving up on the left of 0. So there's my graph. All right, and that ends the second part.